Welcome back, guys. Today let's start where we left off. Yesterday, we managed to get a little bit of understanding of how VFS layer should work, and in general, how it should contact the block layer, and also about the ext front end, because what we have currently in our kernel is that we have the backend, which is the block layer, and block layer can also have a internal layer, which is the ext backend. But from VFS perspective, we also have to have a ext for front end. So VFS layer will connect to the ext front end, and the ext front end will reach out to the block layer, and block layer will internally reach out to the ext backend through which IO. So this is the flow, and yesterday we managed to understand how most of it works. In general, the flow, I've explained it in the study session. So we'll continue with that, and maybe we can let's see if we can implement it. Other than that, in general, we are trying to write our own kernel, and we have been done with the scheduler and a little bit of memory management unit, and also right now syscalls are working, interrupts are being handled, and currently we also finished a little bit of block layer, currently working on the virtual file system layer, and first backend we are going to VFS front end we are going to support is ext4 file system. So let's see how it works. So yesterday I also managed to clone the entire Linux source from Linux upstream, so that we can learn how things are implemented in the actual kernel and try to replicate them in our side. Because as I've been saying from the beginning, this will be completely similar to Linux, but we are just trying to understand things and write it. So it's better to start with the source as Linux. Yeah. So let's in general get an high level picture of how ext4 front end would look like in the VFS layer. Because yesterday we did see some examples here. So we know the front end. As soon as we have the file structure, we are calling iter, and the iter just directly goes into a ext4 function. So this function must be registered by a ext4 front end, and we do the parsing and we get the block. And so there is a front end layer code that has to do the ext stuff, and we have the high level VFS layer stuff. And even only after finishing all these steps will be going into the actual block layer. So this will be the ext front end code that we want to replicate. So first of all, I need to picture it, because I still don't have a clear picture of how it looks, how it will at least fit into the picture. Because from my understanding, so inside Kmain, once I'm done with the block layer initialization, here I'm setting up the which IO block layer. This is just for testing purposes. So the next thing I have to do is I have to initialize the front end, in general the overall VFS front end. So I have to call something like VFS init, and I have to call a particular drive that we want to initialize. So this is what I want to call here. So let's write that. So once we are done here, So what we want to achieve is that we want to init the VFS with a drive. Let's say example VFS init, and then I just call, let's say, slash dev, and my drive, let's say it's ext4. So this is the drive that I want to initialize. Once I have initialized this, then I should be able to call, let's say, some VFS create, let's say test.txt. So this should create create a file in the root inside the newly initted drive. This is what we want to achieve right after we initialize our Virtue backend. So now I need to understand the picture behind this step. Behind this step. So I directly initialize VFS with a directory. Maybe the moment I do that, I need to convert this into a actual file system first of all, because currently so that I guess that just means that I have to go through all the registered backends, because currently I have registered a backend with backend info, right? So then this step, what it does is that it will go through all the backends that are registered, and it will read the 0th block, which is the super block. I'm not sure if you have if you remember it from the previous streams. So ext4 has ext4 file system in general is just multiple groups. So it's like a single contiguous bigger physical block that is converted into smaller groups. So let's say there's group 0, group 1, group 2, and stuff like that. So what this function should do is that it has to go through every registered device, read its 0th group, and check if it is ext4 file system. If it is, I guess ext4 has a magic number in the top, so if it matches, then it is a ext4, and then it can say that it can register it as a drive. And okay, it is possible to have multiple drives, but in our case it's just going to be one drive, so it's always going to be registered as dev ext4. And then we call VFS create. The first step is just going to check this group, and it's going to just say that it's registered. Maybe do you want to add anything else there? I don't think anything else is needed. The second step is the biggest one, because in this case right now we also have to read the internal data, because within group 1, I guess, we have inodes and block data. So we go through all the blocks, and we set up inode as used, so that we can use that inode in VFS layer, something like that. This is the entire, right now we know the internal details, because we know the internal of how it works. All we have to do is that how the flow is going to start. Hi. We just have to understand how the flow is going to start, because from my understanding it's going to have a initialize, and then we have a create, Init is just going to read the block 0 and understand the magic number, and we can confirm that it's a X4 file system. So what happens next is that we'll have to, yeah, this is what I want to currently understand. Okay, let's see here. How do I picture VFS init and VFS create create once I'm done with which block layer in my setup. I have done block layer. I don't know, let's see. First of all, I need to understand once we are done with parsing X4, where we are going to put this information. Maybe we have to store this register this in memory to know that we have initted something, and we'll always hold that somewhere. So VFS layer is going to have the high level functions, which is read, write and stuff, and the concrete file system, and then we have the actual file systems. So when we call user open, okay, this is the high level syscall open with a file name, and we pass something. VFS layer is going to do what? You didn't explain what it's going to do. And then we have the X layer, and then we have the block layer. So this is the entire flow, because currently our block layer just takes a block number and it will read as many as bytes you want, and that is working perfectly fine. And what we want to implement is the high level VFS layer and the X front end for the VFS. So VFS has the super block, and we have inode, we have tent tree, and we have the file. What we have implemented is that we have inode struct. This is still questionable field, and we have the file struct. Yeah, we have both inode and file struct. We don't have dentry. Dentry is just linking inode with the actual string based directory or a file. Superblock is just because let's say you have a VFS object. That object should represent or should be represent in a file, in an actual file system. So you need to know which superblock to point to. That's why we have a superblock object. So I think maybe this layer has my fucking. So what it has to do is it has to init read the superblock of the image, and then I have to probably hold the in memory copy of this superblock and store it as SB superblock inode superblock struct. So we need a superblock struct first of all. Something like we have file, we have inode. Let's just add one more thing, which it should be type def struct, and it's going to be superblock. We'll define it as superblock. Okay, we have superblock. It is going to be superblock. And what are its fields? I know it should have a magic number. So let's say in event 32. Magic number. And probably it will have the number of, because as I said, ext4 file system has multiple groups, so the entire physical block is converted into multiple groups, and every group internally has its own separation, which will be the inode separation and block separation and stuff like that. So yeah, we can implement this later, but in general we also need a super block. This den tree, I don't think we need it. We need to implement it right away. Let's think about it later. As of now, let's just assume that our VFS layer should just work with a superblock, inode, and a file, and we have those structures. And currently our superblock is simply going to have the magic number, and what else? Number of blocks and number of inodes. That should also be a good thing to have. Yeah, we'll update it later. In the kernel bloat, you eventually do equivalent of mount the ext for root. What's the very first VFS object network? So where does it come? From my idea, my current kernel, everything is, we start from start.io, start.o, we jump into kmain, inside kmain I am initting the virtual backend, so I don't have those temporary file systems in my setup. So let's just talk about how to picture the VFS init and VFS create inside my setup. Oh fuck me, I should have said setup instead I typed self. Okay, whatever. But I think overall that is all we need. We only need to pass the superblock, and then we need to know, right? And yeah, this is the file system. So a superblock will have all these stuff. It will have the number of blocks, number of inodes. We have a layout. So this is the layout. So let's get this straight. We have a full contiguous physical memory that, let's say, it's 1 TB of size. That 1 TB size is going to be divided into groups of 128 MB, and every group will have a number starting from zeros, and it will have a group descriptor, data block, inode bitmap, inode table, and the actual data. So group descriptor is just the number of blocks within this group. So this zeroth group can have multiple blocks, which will be data blocks. So it will be just how many blocks are there. I don't know what the fuck is this. And the data block bitmap is to confirm out of all the blocks which block is actually used. So it will be, every bit will represent a block. So if the zeroth bit is set, that means the zeroth block in this data block is being used. And what about inode bitmap? I think inode is also the same thing, but it is not one-to-one mapping. A single inode can hold multiple blocks, I believe. Yeah, because inode table. So if it will just say like how many inodes we have, and in the inode table, let's say if we have inode 1, and we'll know inode 1 will have which blocks, whatever blocks it is holding. So inode 1 can hold block 50 to 60. So inode 1 inode can hold 10 blocks. So maybe that's why we need this table. Yeah. Okay. So overall, this is the structure that we want to picture. And so maybe we want to add those fields here. I'm getting a call. X4 bitmap. So let's just start with how many blocks we have. Event to blocks counts, and tie to inode counts, and then we also have we have the group count, we have the inode count. We need to have bitmap for data block and bitmap for inode block. And how do we represent a bitmap? We can just represent it as a character array, and a single character can have 8 bits, I think. Yeah, 8 bits is 1 byte. I don't even remember that. It's how many bytes? Yeah, it's 1 byte. So 1 byte can hold 8 bits. So we can every character is a byte. So if we allocate a character array of 64 bytes, then it should have 64 into 8, which is around something. But how many actually we need? I think we only have to have 24 128 something, because yesterday I was checking the total number of blocks and stuff. Oh, we also actually have the length we need to use here. Let's see how the bitmap actually looks. Oh my god, actually super block should have all this information. I think if we add all of this, we can simply take the first starting of the super block and just cast it to the structure, and everything should automatically be accessible through the just the fields, or we can use the offset to directly access it if we don't want to create the entire structure. I think in my case I'm not going to create the entire structure, so I'm just going to use offsets. So every I can just simply add some helper function to directly fetch the offset. So in case my super block will just have a starting address, I mean the base address, and I just call my helpers to, if I want to get the inode count, I just call base address plus 0th offset. It should give total inode count. But why the fuck the inode count is in the 0th offsets? And total block count is in the 4th offset. But it's a really big structure. As my bitmap, that is what I'm currently looking into. If we can get the bitmap, what the fuck? There's no fucking bitmap. What the fuck? Okay, it's just going to store the address of the bitmap. It's not going to store the bitmap internally. So we can just say it's a U64. I mean, we can use U64, but in the actual block, it's going to be higher and lower address, because it's like it's all 32-bit registers, 32-bit locations. So the upper half will be in a variable and the lower half will be in a variable. We can just group them together into a 64-bit. I mean, in my example, I think I'm just going to put it as event 64 and make it as inode block bitmap, and I also need inode bitmap. Do I need anything else? I have the magic number. Do I even need the magic number? I think I don't need it. So let's just comment it out as of now. I need the block count. I need the inode count. I need the number of, I need the address of the bitmap, I need the address of the block. Maybe we can put this as structures. If not, every time we have to cast it and then access it. I will think about it later. As of now, one bit represents the usage stated of one data block or inode entry. A group size of 8 into number of bytes in the logical block. I don't fucking understand what is that. This implies a block group size of 8. 8 as in we have 8 bits into number of bytes in the logical block. I think that means that if our logical block, that is the total count is what, let's say 50 blocks, that means our inode bitmap should support 50 divided by 8, right? Why is it multiplied? Fuck me. We'll come back to that. And then we have the inode table, which is also a big thing. It's like documentation is just hurting me in every level. And I guess I'm just going to write a simple inode table for myself instead of writing this entire thing. Actually, we have all the logic already specified here. Even finding a node, you have the logic here for each block group entry. Node is defined. Formula is defined is that you just get the inode number -1 divided by the groups, total groups, and you can also find the index, and we can also find the offsets. Every damn thing is already documented. But from my point of view, what I have to do is that I have to create the simplest version of this file system. So I just understand what is being actually done and what is the minimal setup I could get to get this working. And then if we need it, we can implement anything on top of it. We don't want to implement this whole fucking thing. It's just too much. Okay, let's see what's our answer here. File system, do not RAM only scaffolding, no detached global pointer that will eventually be your, call it root entry right now, null storage for superblocks, inodes entry, registry of file types. What the fuck? For you, that's one entry. Entry is essentially x mounts. Okay, I didn't understand anything. Okay, we'll come here. So here we init it. blocked device is done. Now we want to actually do the VFS. So we store a global variable that is null. It's not yet registered, and we are going to call something called mount roots, and we are going to call as x4 from vblk0, and internally it's going to call block read. As I mentioned, it's just going to do the same thing, because that is all we could possibly do, nothing much. So internally it's just going to read the super of the image. So we take the 0th block, we read the 0th block, and we confirm it's a X disk. And what do I hold in my memory? I have mentioned it as super block. Let's see what we actually want to allocate. VFS super block, fill the S operation with X4 ops. Okay, I get it. So currently what they're saying, what it says is that once we know that it is a x4, that we read the super block and we confirm that it is a x4 file system, we can read the 0th blocks. Yeah, we can read the 0th blocks and data bitmap and inode bitmap. I think so. Yeah, because it says table, descriptor and inode table. Oh, there's something called descriptor table. Where is that? We have inode table. Where is descriptor table? Maybe this is descriptor table. Why do we need group descriptors? Maybe that is what it is. It's going to have every group how many blocks. Here, every inode how many blocks. Okay, we have some questions. So when inside the initial block reads, let's say I confirmed that it is x4 by reading the super block. Now I have to read the inode table and descriptor table from the block 0 and hold them in memory. What is here in this case? The inode table will hold all the inode info. What does descriptor table hold? Okay, I let's just confirm what will be stored in the descriptor table. I think other than that we don't need any information. Next step is just to read the descriptor table and store it in memory. and read the inode table and store it in memory. That is all we have to do. Hold on. Fuck me. Am I wrong? You need to read the whole inode table into a real X4 file system. The node table is enormous. Oh, okay. We will only store the inodes that we are currently using. So every time we need a new inode, we just directly go into the disk and ask it. But that would be also like really costly, right? So every time we create, and maybe that's why every time we create a new file, the operation takes more time. Also, every time you, like one of the biggest questions I had back in the day was how is copy operation so fast and move really slow? And the answer was that copy operation only has to move an inode object from memory to a different part of the memory. But move also has to move the data from one physical block to a different new physical block. So that is okay, but still in my case, let's assume that we are only going to copy the inodes that are used currently and keep them in memory. So we start by reading the super block. We know that we can get information like block size, group size. We'll also confirm if it is actually X4, because only X4 will have a super block. Other file systems won't have such things. And then we have group descriptor table, small, needed every time you allocate, find any inode or block. What the fuck is this? That was my fucking question. We know that we have block bitmap, inode bitmap, and we also have table blocks, and we have. So I think this group descriptor is also a table. This is what it says here, GDT. But it says here it's GDT, reserved GDT blocks. Maybe this is the actual table, maybe this is something else. And this response almost matches with this setup. Okay. Load the inodes table is no. Don't X reads inode by computing where the inode lives on disk and doing a single block read. Okay, fuck it. And I know disk layout. Okay, this is the biggest layout that will be useful for us. X4 chops the device into block groups. As I mentioned, the physical block will be physical thing will be converted into lots of groups, and every group is converted into lots of blocks. So each group is a self-contained mini file system of its own bitmaps, own inodes, and own data area. The first block group also holds the super block and GDT. Okay. So we have the 0th block, which is reserved for the super block. This super block information will have some overall metadata about the entire thing. Okay, so this group descriptor is about what are the actual blocks are currently being used, like not what are the groups that are being currently used. not blocks. What the fuck? Array one entry per block group. Okay. I think it's overall block. So in group 1, there will be block x2, x3. I want to allocate a node. We check GDT for a group with free nodes. Then that entry tells you which entry in the block holds the inode bitmap, and then we read the block and we scan the bits. The only thing that makes block groups discoverable. Hi. Without that, we won't have a formula. So overall, the entire group structure will be present in this group table. And whenever we want to allocate a new node, we have to come here, ask this table to find a new group first of all that has free nodes, and then we go to that group, go into that node, and we assign that node. Or in case we want to read, we just do the same step and we read from the node. So overall this picture is correct, and I guess only thing that is missing is the table here, and only thing that's missing from our where is it? Yeah, we can add the two tables. So it's going to be pointers, not we're not going to follow the same structure as Linux will do on our own. So let's try. It's just going to be block table, and it's going to be block table and inode table. So we have block table and inode table. These are both will be both addresses pointing to the actual table, and this will also be addresses pointing to the actual table. And we have the count. Do we need anything else? If we parse this field, we can get information about how many blocks are possible, I guess. Well, let's also put that. It should be super block. I mean, this is the fucking super block, right? Then why the fuck does it internally have? Maybe this is for overall for every block, not just our block. Then we need to move this to a block. Okay, let's do that. Let's see, let's put type the structs and define just a normal block, a group. Yeah, a group will have a super block. So yeah, I think it's a group. X4 group. That should make sense. And we paste it here, and we can have one more field which will be the struct. No, we can just put super block. It's going to be super block. What the fuck? Okay, now we have a X group, and it has a super block, and it has multiple tables. And now we can actually represent one full group, and we can have multiple groups. A file system. And maybe we should also create a structure for blocks, because blocks on their own will be separate. It will be X4 group, and detective should be X4 group block. And it should be X4 block. Okay, what should a block have? I think block should just have data. It's simply void star data or character star data. I think, yeah, it should not have anything else. Let's, instead of putting character, let's put uint 8. So it's going to be just 1 byte, 8 bytes, or 1 byte, 8 bits. Yep, that should work. Now we have the structures to represent this entire thing. So we have the actual X4 file system's bigger block, which is the group, and group can, only one group will have the actual super block. The rest of them, I think these two blocks will be left empty. I'm not sure, we'll confirm that. But other than that, every group will have a group descriptor, and we have 2 bitmaps and inode table and the actual data blocks. So we can represent everything as of now. Maybe we'll need to fill up the information here, but overall I think this is all. Yep. And we can also have one more structures. There's like this operations, and we need to change this to file operations, not just operations, but file ops. And then for file we have file operations. I think it should be a pointer. Yes. Superblock does not have any operations. We do have group operations, I guess. We will have group operations and we'll have a separate data block operations. So let's create that. We'll have def structs. It's going to be group operations, OPS, whatever operation we want. Fuck. It's going to be group operations. And currently it's not going to do anything. We don't know yet what sort of operations we need, but I'm sure we need operations. So it's going to be group operations pointer ops. I think it should be good. Yep. Okay, now let's go back to the theory and see if we have as I said, we have multiple blocks. We have the group descriptor table, we have the inode table, and we also have two bitmaps, and we have the actual data blocks. Now we have two questions. Does other groups actually have these two entries? In other groups, example group 1, 2, do they have block 0 and block 1 left empty? So we have block 0 in group 1. It's not absolute block 0 block. Okay, so it's not like every group gets its own block 0. It's just keep on numbered. Okay, that makes sense. So it's simply every group is going to just keep on incrementing the number. So we have a 0th group that has the 0th block and the first block. Every other group is just going to continue from the previous block. Okay. Then it would make sense to have one table. That means only group 0 will have this block table. No, only group 0 will have the GDT, which is supposed to be inside so we have GDT, and for For the rest of them, we just start with block bitmap and inode bitmap and then inode table and then data blocks. Only the first one. Okay, also backup holding groups will also have zeroth and first block used. In the actual first group, there will be the zeroth group, zeroth block that is used up. The first block will be used up, and the second block will also be used up. Third block will be used up, and then we have the data bitmap, inode table, data table. And in every other node, if it's a non-backup node, then it would just have the bitmap and bitmaps and inode table and data blocks. If it is, I guess we need to write this down because it will be needed for future reference, because we can't recall everything every time. So X for block 0 will have the super blocks and GDT, and then the bitmaps and table and data blocks. Group 0 block 0, it should be a tuple. And now let's go to group 1 blocks block n plus 1. Block numbers are incremented across the groups. So we'll have, in case this is not a backup node, then you will have the bitmaps, table, and then data blocks. And let's go to the other case, which is, let's say, group 50 and block n plus 1. In this case, let's say it is a backup node, then it will have zeroth. What is SP? I don't know what the fuck that is. Okay, something called SP will update this. And then we have backup GDT, which is global GDT but backed up. And then we have block bitmaps and table and data blocks. Okay, so what the fuck is backup SP? Was was backup SP mean data in the group that serves as a backup. Okay, it's just going to have a copy of the actual superblock. Original copy of the superblock. Now it makes sense. It almost is like the zeroth block, but it has just the backup plus the actual bitmaps table and the data. Okay, makes sense. Okay, in case if the group 0 gets corrupted for some reason, we can just go to some group 3 or somewhere it is actually backed up, and we can copy everything into the group 0. Okay, it's all good. It's all good. We don't need this information yet. Let's get a full example from X4 calculations for, let's say, 4 GB size with 4 KB blocks. Let's see. I think only thing left for us to understand is example of how things work within this, and then we can also build the operations that are needed, and then we can actually write the code. So we have a device size of 4 GB and we have a block size of 4 KB. So every block is of 4 KB. So there will be total of the 1 lakh. I guess it's 100,000 K something blocks per group. Okay, so the actual bitmap size will be equal to the block size. Huh. Makes sense. So a group can only hold as much as number of bits in the block. Okay, this information we actually needed it because how much is the size of these tables? Let's write it. The size of the tables will be 8 into total bytes. Because a single byte can hold 8 bits. So no, size should be actually total bytes divided by 8. The block size divided by 8, and the number of blocks we can have is the 8 into block size. I think so. If the block size is 4096, let's see what is that. If we go to Python, the fuck is it should be 4096 divided by 8. It should be 512. So we have to. So if the block size is 4 KB or 4096 bytes, then block table will be of 512 bytes. Five 12 bytes are bits. I think 512 bits. Yeah, 512 bits. So 512 bits into bytes. Fuck me. I don't know. I think so. It's 512. So it's 64 bytes. We need only 64 bytes. We need a 64 bytes table to represent what is it? 8 into, so it should be 8 into 4096. Total blocks that we can have is 32768. So we need 64 bytes to represent 32768 blocks. Hopefully my understanding is correct. Let's just confirm it. Is my understanding correct? I think if we can half correct what the fuck? Walk. What the fuck did I get wrong? Block bitmap only uses 1 bit per block. Okay, fine. So we have 8 bits. So if our block size is 4, then it occupies one. So it's like 300 and okay, 32,000 blocks are representable. Bitmap is one full block, so it is. What the fuck? What the fuck did I even say for the 64 bytes? If we have so our table size, our block size is 4 KB. So table size should also be just 4 KB. Block table will be of. Why did I even write this line? Block table will be of 64 bytes. Our table size is actually block size is 4 KB. So if we multiply it with 8, we get the total number of blocks we can represent. Actually, my assumption is completely fucking wrong. I was thinking like if my block size is 4 KB, then that is 4096 bytes. Then and 1 bit represents a block. 8 1 byte has 8 bits. Then 8 into 4096 is the number of blocks we can represent. And I was thinking, like if my then the size should be size of the table should be 40 size should be I don't know. I don't fucking know. How did I even write this line? block table will be of 64 fucking bytes. I was like taking 512 as bits. Oh, this is just so fucking. Should be of 4096 divided by 8. That is 512. But 512 is number of bits, so it is of 64 bytes in size, the table. So I was like, so finally 64 bytes of table can represent the entire 4096 into 8 blocks. This is so fucking stupid, but this is what my idea, and which is currently wrong, I guess. Which is sad. How big is my bitmap block itself? My block size is 496. So there is 32,768 bits. So my 4 KB bitmap block contains this many bits. How many blocks does that cover? 1 bit covers 1 block. So I can cover 32,768 blocks. That is it. There's no fucking division after that. Okay. I think I should have fucking stopped there. I'm just fucking confused. Yeah. I just fucking confused things myself. Okay, so let's just redo this. So the size of the table will be block size. No, the size of the table will just be the block size. There is no division. Will be the actual block size. And the number of blocks can be, we can have is the 8 into table size. Maybe we should use table size here. For example, if the table size is 4096, then 8 into 4096 is the amount of the number of blocks we can represent. That is all. Okay, I think it's fine. Okay. Okay, what else do I need? I start from x4 I can read different blocks now. I also know the size of these tables. I know the size of the table. Right, will be the size of bitmap, and what is the size of table inside a group. I think both are just 4096. That is the size of the block. Inside one block group, there's three structures. We have block bitmap, which is also just the same size, which is 4096. So 1 bit per data block. And then we have inode bitmap, which is 1 bit per, even though only, okay, it is also still going to use the entire block. Okay, we have to understand how inodes calculated. An inode table is 512 blocks. Okay, we did not know this information. And so we have the block bitmap, which is one block, which is 490. So we have this many bits. And we have inode bitmap, which is also the same size, but it will only use 801 something. I don't know where this number came from. We'll ask that. And then we have the inode table, which is of 2 MB. So inode table will actually take 512 blocks. And then we have the data blocks. Okay. We have block bitmap, one block, inode bitmap, one block, inode table, which is 512 blocks. So metadata alone takes like 514 blocks. For backup holding, so there's 512 actual blocks. Your Visual Studio is not running. See, maybe you should just try using GCC or Clang. Check if you have installed it, and don't use Visual Studio. Yeah, Visual Studio Code you can use. You can just build it outside the Visual Studio. You don't have to use the internal VS Code config or whatever that is. Okay, people do use run. I don't know, I have never used that. You can simply put something like just put clang test.c, test.o, and put the file name. You should be able to compile it and run it. Something is inside my test. I didn't know that. What is that? Okay. Oh my god. I don't know what that's. But yeah, you can just compile it this way. What the fuck? Alright, it's into. Okay, now I have one question, which is where did this 80819 come into? What is this number? How did we? How did we know that our inodes can only have this much? Bytes per inode. By default, text on normal file system is 16,300 bytes per inode. What the fuck? So it's just a random number that we decided that we don't want to have this one-to-one mapping. I don't understand. But why? I don't get this picture. But why do we have to follow this? Put this into perspective of my 4 KB block setup. A 4 KB block is the one that we chose. That's fine. But do we choose the inodes per group? Why do we, and how do we actually choose it? Because blocks, that's performance reasons. You can convert it into smaller blocks of 4 KB so that it will be easy to put them into catch. If you have bigger blocks, then you can't put the entire block into a catch line. But if you have smaller 4 KB blocks, then you can actually put them into a catch. That's the reason we choose smaller blocks. So what's the fucking reason for this? Why X forces you to choose at all? Yeah, nobody. Inodes are pre-allocated. In X4, inode table is carved out of time and never grows. Lays slots in your cannot add more later without reformatting picture. Inode. Okay, so this is the reason. So this way we can reduce the metadata. Okay. A single inode on its own is going to take up some space, right? So to reduce the overall size and actually use the space for something valid, only for that reason we actually go with this approach. So overall, for 4 GB space, we'll have like two 260K slots for inodes, and every inode is of how many bytes? 256 bytes. So it will already add up to 67 MB. Okay, I did not understand anything, but I have one question, which is why is inodes consuming 256 bytes? Well, if only if we know these things, we can build a picture on our own. So that is also a fucking default value. So that is just the metadata, the actual metadata that we want to hold within the inode, like permissions, timestamps, etc., etc. So currently, a single inode can store up to 256 bytes of extra data. Okay, not bad. So that means within my inode, where is my fucking inode? Okay, that's why I have this data fields. Now it makes sense. Maybe, I don't know, let's just convert it into metadata. Also, metadata should be some structs. Inode metadata. That would be easier. Let's type that. Metadata. Data. It will be inode metadata. And whatever we put here can only be of 256 bytes. Currently, there's an upper limit of 256 bytes. And inode. I think it's overall inode, so maybe that means this should also be considered as part of this 512, 526, 556, 256. Okay. Whatever. Let's put character name, and its name can only be of maximum 64, and UN64 created timestamp UN64 last modified. What the fuck? Created last modified name. What else do we need? I think we can have it as character star, so it will be maximum only 64 chars. We have timestamp, we have last modified, and we have name, and let's also put some permissions. Permissions will also be just U32. I think use 8 is enough. Permissions. Okay, now we have inodes with metadata. And okay, it should be stored within the block. So that means this structure is only to hold that in my internal memory, so it does not matter. I can just have it as pointers. Yeah, I think we have everything else. Let's make it as pointers. Only thing left is to define the mm, super block a little bit more, and we need group operations. Probably we also need block operations, because init is going to group operations. The first operation is let's put void star. How do we define a fucking function? We would return a function pointer, and it's going to return uint int eat, because we need minus value, and then star what do we name it? We can name it as read super block, and it's going to have, I think maybe we should put pointer here. Oh, fuck me. This is with points here. Oh, function pointers are pain in my fuck. And input should be, it should just take what should we read from? I think we can just take X group as inputs. Yeah. X group. What? X group as input group. Do we need anything else? I think that is all we need. And it should read written as true if it's actually a super block, and everything else should be directly added to the super block fields. We won't return anything, it will directly update its own, because we are passing self here, so we can just update that block. We need update block bitmap, update inode bitmap. A read table, update table. Oh my god, we need lots of functions. And almost everything is going to be the same setup, and it's going to be read file bitmap, group bitmap, block bitmap, and inode bitmap. So it's inode bitmap and we're going to read block bitmap. And we can have I know table. I think we should also improve the input variables, input arguments, and it should be block table. And maybe read block will have, what will I actually have to read from a block? If if I have a block number and if I have to read from it, actually read from it, first of all I have to check the block table to see the physical block mapping. So we go to the block table, we check if the block we get the block's physical block number. I think so. So it can take block number 32 block number, and it will be not physical block number, it will be which it's like logical block number, not physical block number. Maybe I'll just put logical. What else? I think we have a good base. Oh my god, it's already 1 hour 53. Okay guys, so today what we have done is that we have little more understanding of how ext4 works. We have also converted the ext4 into little more of our actual structures, and we also know a little more of what to read and how it will be actually be presented within the block. We just keep on building on our understanding of how ext4 file system works, and how the structure internally works, and how we are going to represent those structures. And we are still working on it. Yeah, let's keep up with this. Nothing much. See you guys tomorrow. No, see you guys next week then. Bye. What the fuck is it?